Kinopio to Markdown. Status December 4th, 2023. The URL is in the README. It's public read-only. Basically, there's only several cards on this page. The main card has 2 branches. Each branch has a tree of sub-branches. The desired result is a Markdown file in point form, indented properly. To get from the Kinopio format to the Markdown format, export the Kinopio to JSON and then run it through a small program structured as 6 components. Some of the components are very small, but it's nice to get them out of the way and not have to think about them. Write and forget. Chip away, make the problem smaller. The smaller the pieces become, the easier they are to implement. The first component just reads the text file. The second component escapes the white space in strings and comments. The third component calls the JSON to include only the stuff that's semantically interesting. It removes all the graphical information and all the stuff that I'm not interested in for this particular project. This step could be replaced by JQ. The fourth component transpiles the JSON cards to Prolog rules, creating a fact base. This component is written in OM.js and RWR. I'll describe how that works later. The fifth component creates Markdown from the fact base. This is written in Prolog. Prolog does pattern matching and exhaustive searching. It's looking for connections between lumps of text and deciding what the root of each set of points is. When it finds a root, it prints out the subtree connected to the root. Finally, we clean everything up by unescaping the white space and outputting the final result. To run the tool on the exported JSON, we just run make. The red box named question mark is a probe that shows data as it flows by. The culled JSON is converted to a Prolog fact base. For this project, I'm only interested in blocks of text and connections between them. I create text facts that include a machine-readable unique ID and a string with spaces escaped. So every piece of text is represented as a string with an ID. I create connection facts that tie the text blocks together. I drew connections in Kinopio, making connections between Kinopio cards in the usual Kinopio fashion. This format is reduced to Prolog connection facts that contain 3 IDs: the source text, the target text, and the unique ID for the Kinopio connection type. At this point, I simply ignore the Kinopio connection type information and assume that every connection is a Markdown indentation. Later, if I have time, I might try to recognize some connections as footnotes, others as comments, and so on, but not now. I'm only interested in source IDs and target IDs in connection facts at this time. The step labeled transpile cards to Prolog writes these facts out to a local file called content.pl. The fifth step runs the Prolog program, which figures out the translation from facts to Markdown. The program itself is called md.pl and can be found in the main Kinopio2md directory. The program first reads the fact base using a command consult content. Then it runs a number of very simple pattern matches against the fact base. The search is recursive and finds all of the possible matches as specified by my program. This is what Prolog does well, exhaustive search, using very little syntax and very few lines of code. You can do this by writing loops within loops using some other language, like say JavaScript, but Prolog makes it easier to write and to get it right without missing any edge cases. The gotcha with Prolog is that it uses backtracking, which used to be considered insanely inefficient in the 1950s, but on today's hardware, it runs fast enough. To my eyes, it looks like it finishes instantly. I don't care if it took 100 microseconds instead of 100 nanoseconds. I can't tell the difference. I guess I would care if I sold this to 1 billion people who didn't have computers as good as the development machines I've used since about the year 2000. The other gotcha with Prolog is that you need to change the way you think. You can't write code in the usual imperative manner. You write code that says what to match for, and the Prolog engine takes care of finding the matches for you. You can't tell it how to do matching. At first, I was puzzled, but Now I can't imagine doing pattern matching any other way. The important component of the Prolog program is the for all statement, which tells the Prolog engine to find everything that matches the isRoot pattern and then run the printRoot rule on each of those matches. isRoot ID is nearly trivial. It says that a root is any piece of text that is not a child. Let's take that apart. Start at the isRoot rule. It has only 2 lines of code in it. All of the lines of code have to be true for the rule to succeed. When the rule succeeds, it sets the variable ID to the ID of the found text item. The pattern is 1. The ID must be a text ID. 2. The ID must not match isChild. That's pretty concise. Now let's look at the isChild rule. It is also ridiculously concise. It says that an ID is considered to be a child if there is any connection fact that includes the ID as a target. Prolog finds one match at a time, then backtracks. The programmer needs to ask Prolog for each match. At the command line, the programmer uses the semicolon key. In code, the programmer uses the for all rule. The end. That's the code for figuring out which IDs are roots. 3 lines of code. Next, let's look at the rule for printRoot. You'll see 2 contiguous rules called printRoot, and that's already different from the way we're used to writing code. One version of the rule specifies how to match a printRoot, and the other version specifies a different way. The Prolog engine just tries every rule over and over again until it can't find a match. In other programming languages like JavaScript and Rust, etc., we would use loops within loops and or expressions. And we'd probably miss some edge cases along the way or inadvertently insert bugs into our code. In this case, our first printRoot rule says print the node and then to print the tree for each child. The second printRoot rule handles the edge case where a root doesn't have any children. If there aren't any connections with the root's ID as the source, then the root doesn't have any children and we just print the node and finish. The rule print node just punts its work to the print text rule. Print tree prints the text at each level preceded by a dash. Print node and print tree track the indentation and print 4 spaces for each level of indentation, the standard for Markdown indentation. The root has an indentation level of 0. Each successive call to print node increments the level. The net result is that the code prints each node at a given level of indentation, along with all of its children at the next level of indentation. This happens recursively, so the children of the children are indented beneath each child. The recursion happens in a depth-first manner, so that a fully indented subtree is printed in its entirety before any other subtree is printed. Future, moving forward. The Prolog code was grown incrementally. It could probably be rewritten and refined. I want to see if JQ can be used to replace some of the steps. I want to try bigger and bigger Kinopio spaces.